part 2 of section 10.4. So we left off, we found a Fibonacci number without having to go through the whole recursive process, a big time saver. And now we're going to look at some amazing facts here. So one of the things that's amazing is how much Fibonacci numbers show up in nature. Pineapples, sunflowers, daisies, many other plants have characteristics that when counted are Fibonacci numbers. It's just mind-boggling. Mathematicians geek out over this like you wouldn't believe. And they also lead to one of the most eye-pleasing ratios known, this thing called the golden ratio. Before we get to the golden ratio, I do want to show you some of the things where Fibonacci numbers show up. So here we have a flower, and looking at the spirals, you can kind of see, there's spirals of seeds kind of going in and whatnot. And if you count the number of spirals that are curling out and then kind of pointing to the right, there's actually 34 of those, a Fibonacci number. And if you count the ones that are kind of curling out and then spiraling, I guess, counterclockwise, pointing, if you're looking up top here, they're kind of pointing out to the left. There's 21 of those, another Fibonacci number. It's just mind-boggling. And if we look at a pineapple, there's a lot of different ways you can count them on pineapples, but you'll see like there's 5 going around that way, 8 going in this diagonal, 13 going in that other diagonal. Just pick up a pineapple sometime and follow the row, the kind of natural row of those little spiky things on there, the skin, and it's going to be a Fibonacci number. It's just crazy. So let's see this one here, pine cones. They got them. There's 13 spiraling rows of the little pine cone spiky pieces. I'm not sure the fancy name for that, so I'm just going to call them the spiky pieces. They always hurt when I pick them up, or at least poke me. So there's 13 of those. That's a Fibonacci number. It just goes on and on and on. Again, if you just Google this thing and look for Fibonacci numbers in nature, it just keeps scrolling and scrolling and scrolling. They're everywhere, and it's amazing how much they show up. So anyway, let's move into the golden ratio, and I'll go back over there. There's a couple of things with this that I want you to see too in nature and in architecture. But basically, if we consider what happens when we find the ratio of consecutive Fibonacci numbers, 1 over 1 gives you 1, 2 over 1 gives you 2, 3 over 2 gives you 1/2, 5 over 3 gives you 1.6 repeating, 8 over 5 is 1.6. So I want you to kind of notice what happened. We started at 1, we went to 2, then we came back down, then we went up a little, came back down, went up here in the next one, 13 over 8, 1.625. And then we come down a little, 21 over 13, 1.61. But after that wild fluctuation initially, a whole 1 we jumped and then down a half, kind of honing in on a 1.6. And as you keep going through this row here, still stays 1.6. And it looks like it's staying at 1.61 all the way across. And we get down here and it looks like we start locking in that 8. Start locking that in. And the 0 maybe even. And then if you keep going, you get this number. It's kind of like pi, kind of like the number e. It's a number that goes on forever without repeating. And you get this golden ratio. Phi is equal to 1 plus the square root of 5 over 2. And the decimal approximation is this 1.61803398887, etc. Before I move forward, I want you to recognize that that number right there was a key aspect of us being able to get a Fibonacci number without having to do the recursive process. So there's something to that. I'm not going to go through the derivation of it, but it definitely plays a role. So in art, a study was done with rectangles, and rectangles that had the following ratio of sides or very close to it were voted as the most eye-pleasing. Somebody actually did this study. It's kind of crazy. And the ratio here, if we look at the long to the short, so you got A, this is A here for this little rectangle, you got A over B equal to, for the bigger rectangle, the long side is A plus B, and then the short side is A. And if we just let A equal X and B equal 1, then you're going to get X over 1 equals X plus 1 over X. So I'm kind of solving for the A that would be needed to give me this ratio. And if I cross multiply, I'm going to get X squared equals X plus 1. If I move everything over to one side, I get X squared minus X minus 1 equals 0. And then we use the quadratic formula here. So the quadratic formula, and I'm going to have to write this in right here, sorry. Quadratic formula is X equals the negative B plus or minus the square root of B squared minus 4AC all over 2A. And you may or may not have seen that before, but the idea is that in this case, A equals 1. It's always the number in front of the X squared. The number in front of the X term would be a negative 1, so that's the B, and then C is always the constant. And if you plug this in, you're going to get 1 plus or minus the square root of negative 1 squared is 1 minus 4 times 1 times negative 1 all over 2 times 1, or just 2. And when you work this out, you get 1 plus or minus the square root of 5 over 2. The golden ratio. So that's where it basically comes from, that if you're looking at these rectangles where the A plus B side has a ratio to A that is this golden ratio, then you're looking at a golden rectangle, as they call it. So we don't use the negative here because it's length. So the negative gets kicked out, so I'm just going to erase that. No negative, it's a length. Square root of 5 is bigger than 1, so it would make it a negative number. But if you were to take that then and just look at it here, and in this rectangle A over B, A to B is going to be that golden ratio. So essentially they're finding that this rectangle right here has the most pleasing ratio to the eye. It is a nice looking rectangle, but anyway, so if you're ever out in art or anything like that, you might want to look and be like, does that ratio show up in places? And in fact, it shows up in architecture. The Greeks knew about this. The Greeks just love this stuff. And the Parthenon has, the overall, the height and the width of it fits a golden ratio. It fits the golden rectangle. And, they got this one broke down a little more, but these smaller ones aren't necessarily golden ratio rectangles. But if you were to look at more Greek architecture, Greek art, you can, again, search golden rectangle in art, architecture. You'll see it show up in all kinds of places. It's pretty crazy. So even more interestingly, when the smaller rectangle is split according to the golden ratio again and again, and the corners are connected in the right way, we end up with what's called the golden spiral. And that's what's happening here. So you see you got the big rectangle, it has a golden ratio. Then they put a smaller one inside of here, it's got a golden ratio. Then they put another one right here, golden ratio. Then they broke it up into this one, golden ratio, then this one, golden ratio, then this one, golden, and et cetera, et cetera, et cetera. And then when they went to the smallest one, in the right, kind of in this little middle area here, and started growing out from that smallest one right there, they formed a spiral as it came out, going through all these different pieces of, the golden ratioed rectangle, the golden rectangle. This golden spiral also shows up in a variety of natural settings, nautilus shells being probably the most common example. But again, let's look at this and see. So here's one. This one's crazy. It's a spiral galaxy, and golden ratio, there's actually two golden rectangles here, and the spiral coming out almost like perfectly matches the golden ratio based golden spiral. It's just mind-boggling. It's crazy, and at the same time beautiful. And here's some other ones where the nautilus shell down here on the bottom left, as you curl out, that's golden spiral. They got the galaxy one again, hurricane spiral. This plant, different plants have that spiral in there when you start looking at it. It's all golden, that golden spiral based on the golden ratio, golden rectangle. It's crazy, and this is why it shows up in text. So at any rate, that is something that I hope you now understand and maybe appreciate. You can certainly Google this more and see more examples and look at the beauty that is the golden ratio. On that note, I will sign off, and if you have questions about anything, please ask.